So now let's take a detour and refresh ourselves on some very fundamental concepts, and also some concepts that we might have a bit of a hard time to grasp, but is very important for us to fully grasp before we present PCA. The first few slides might seem a bit silly, so bear with me as we go through it, but we're really just slowly ramping up. So let's start with some very foundational definitions, starting with vectors, spaces, and norms. Vectors represent quantities that have both magnitude and direction. And throughout the course, we've used the notation, the bold notation like this, which meant that a vector was composed of different parts. In this case, if it's in d dimensions, it has d coefficients in its vector. Of course, there are different operations that we can apply on vectors, like addition and scalar multiplication. And I'm sure that every one of you in your sleep can compute the expression that we have here. So if you can't, maybe go at it on your own time and arrive at the same number. Now, what are then vector spaces? Vector spaces are collections of vectors that can be added together and multiplied or scaled by numbers, which are called scalars in this context. We had different ways of measuring vectors as well, and one of those ways was vector norms, which measured the size or the length of vectors. We saw the L2 norm, or the Euclidean distance, be defined as one case of an LP norm, which was the square root of the squared sums of each individual coefficient. More broadly, we had this definition of LP norm, and right now Shima mentioned the L infinity norm, which can be written as the max over x1 to xp, or is it x? These should all be d, so xd. The max value over this is defined or captured by the L infinity norm. Okay. Besides measuring individual vectors, we also found it important to understand the relationship between vectors. And one of the important relationships was called the inner or dot product between two vectors. So the inner or dot product can be written as this expression up here, which is the sum over all the element-wise products between the different dimensions, or compactly as the sum you see there. Now this measured not the length of one vector, but the length of the projection of one vector onto another. Right? So if I have, for instance, two vectors, 1, 2, 3, and 4, 5, and 6, of course, this is a three-dimensional space, then I can write down the inner product, which corresponds to the projection of one onto the other, and it's symmetric, or the projection of the other onto the one, and it gives me, in this case, the value that you see on the slide. Now, further understanding the relationship between two vectors is important because there are some very important special cases, including vectors being orthogonal if their inner product is 0, or vectors being orthonormal if not only are they orthogonal, but also their norms, norm 2's, let's say, are equal to 1. This means they are unit vectors, but also they have, let's say, a 90-degree angle. They're orthogonal to 1. Orthogonality is something that is wonderful if we have in many cases, but it's sometimes a very strict it's difficult to obtain, and it's probably stricter than we actually need. But an intermediary step is linear dependence and linear independence. So what is linear dependence? Linear dependence means that there exists a non-trivial A and B such that taking a linear combination of the two vectors, that means A times V plus B times W, scaling each of the vectors and then adding them up, comes out to 0. If there exists such a non-trivial combination of A and B that gives us this, that means that the two vectors are linearly dependent. If there does not exist such a combination over all possible A and B's, that means that the vectors are linearly independent. Okay, so now here's a couple of questions for you. Are all pairs of orthogonal vectors linearly independent? And are all pairs of linearly independent vectors orthogonal? What do we think? Yes, Guru.
So the first question answer is yes, because if the vectors are orthogonal, then they cannot be expressed as scalar multiple of each other.
Okay.
Sorry. Yeah. So orthogonal vectors are linearly independent.
I agree with most of what you said, except the part where you said they cannot be written as scalar multiples of one another. Remember, linear dependence does not mean that we have one vector being a scalar multiple of the other. They need not point in the same direction. It's about the combination of them that comes out to 0, but they don't have to be always in the same direction.
Okay. Yeah.
So, but I agree with the first part of your answer, which is that yes, for all orthogonal vectors, for all pairs of orthogonal vectors, they are linearly independent. One example, of course, this is an example, it's not a full proof, is if I have these two orthonormal vectors with a 90-degree angle, they're orthogonal, and there does not exist any A and B that you could write that cancels these out for A and B being non-trivial. What about the other direction? Are all pairs of linearly independent vectors orthogonal?
No.
Okay, why? Can you give me a counterexample?
Because linearly independent means you can't substitute one vector with other. I mean, you cannot express one with another scalar multiple of others, and that does not have any kind of relationship with being orthogonal. I mean, orthogonal means dot product is 90 degrees. So those two do not have any kind of relationship. So I think it's wrong.
So let me maybe give you an example. I'm going to say V is equal to 1, 1. So my V is 1, 1. And my W is 1, 0. W is 1, 0. Are these two linearly independent? Can someone come up with an A and B that when you take the linear combination, it becomes a 0 vector? I think you'd have a hard time coming up with that. Because this coefficient is 0, so the only constant that you can scale this by is 0 itself, and then you get a non-zero value here. So there's contradictions. These two vectors are linearly independent of one another. But are they orthogonal? No, right? Because even in this two-dimensional space, the angle here is 45. It is not 90 degrees, and so it's not orthogonal. And you can put it into the inner product, and you'd get a non-zero value as well. Right, so the answer was yes for all pairs of orthogonal vectors being linearly independent, but not all pairs of linearly independent vectors being orthogonal. And so this also goes back to what I said about orthogonality is something that's nice to have, but it's more strict than having linear independence. And many times linear independence is sufficient for us. Yes, Mustafa?
Minus 0.5 and 1 will give us the 0, right?
Sorry?
Minus 0.5 and 1, linear dependency case.
So you're saying that minus
V times minus 0.5 and W times 1.
Okay, what does this give us?
0, linear dependency.
Sorry, but this is 0.5 and minus 0.5. No? Am I doing the sum correctly? It should be giving us a 0 vector, not a non-zero vector.
Okay, sorry.
Excellent. And again, I want to emphasize that the values of A and B have to be non-trivial. Of course, if you set A and B to 0, then that's a trivial value, but that's not the definition of linear independence.